So good day class. So today we're going to discuss about site drainage. So site drainage is necessary to prevent erosion and collection of excess surface water or groundwater resulting from new construction. So when you say surface water, it's from the rainfall which runs over the surface of the ground, and this water carried by an aggregate except that held by absorption within the aggregate particles themselves. Then we have groundwater, which is water near the surface of the ground, which passes through the subsoil. So there are basic types of drainage. So that first is the subsurface drainage, which consists of an underground network of piping for conveying groundwater to a point of disposal, as a storm sewer system or a natural outfall at a lower elevation on the site. Excess groundwater can reduce the loading capacity of a foundation soil and increase the hydrostatic pressure on a building foundation. Waterproofing is required for basement structures situated close to or below the water table of a site. So in my experience class, I think it was a few more than a decade ago. So when we did some digging on the site, during the construction of a housing project in Hasaan, what we discovered was that the site was filled with water. So we had to redesign the foundation because uh, what if the area is wet? So there's a tendency that your building might sink. Okay, so we had to work with a structural engineer to redesign the foundation of the project again. So that's why it's really important, class, someday in your construction to make first an investigation of the soil conditions of an area before proceeding with the uh, building. Okay, so let's move on to the types or the components of the subsurface drainage system. First, we have the catch basins. I think it's discussed in our plumbing. These are receptacles for the runoff of surface water. They have a basin or sump that retains heavy sediment before it can pass into an underground drain pipe. Then we have what you call the culverts, which are drains or channels passing under a road or walkway. Then we have the foundation drainage tile or pipe, which is a tile or piping for the collection of subsurface water, dispersion of septic tank effluent, and the like. Then we have the drainage tile, which is a hollow tile, usually laid end to end as piping in soil in order to drain water saturated soil or used to permit fluid in the hollow tile pipe to disperse into the ground as in an absorption field. Then another type is letter B, which is the surface drainage. So it refers to the grading and surfacing of a site in order to divert rain and other surface water into natural drainage patterns or a municipal storm sewer system. So grass and lawn areas are sloped 1.5 to 10%, while paved parking areas 2 to 3%. A holding pond may be necessary when the amount of surface runoff exceeds the capacity of the storm sewer system. Okay, so I think you're familiar class with there at USTP. So they have a holding pond in the design. Then the components of the surface drain systems are the swales, which are shallow depressions formed by the intersection of two ground slopes. So it's designed to direct or divert the runoff of surface water. Grass swale slope 1.5 to 2%, while paved swales 4% to 6%. Then we have what you call the area drain, which is a receptacle designed to collect surface water or rainwater from an open area. Then you have the dry wells, which are drainage pits lined with gravel or rubble to receive surface water and allow it to percolate away to absorbent earth underground. It's also called an absorbing well. And you have ponds and marshes. They're designed catchment areas for surface water. They have absorption field or disposal field, which are a system of trenches containing coarse aggregate and distribution pipes through which septic tank effluent may seep into the surrounding soil. Then we have what you call an absorption trench, which is a trench containing coarse aggregate and a distribution tile pipe through which septic tank effluent may flow covered with earth. So next we're going to discuss about slope protection and retaining structure. So the need for stabilizing a sloping ground can be reduced by diverting the runoff at the top of the slope or by creating a series of terraces to reduce the velocity of the runoff. So if it's too steep, as you can notice, the flow of water would be very fast. It has a high velocity. So what you can do about it is you can either make it into uh, um, step pattern. Okay, you have to uh, reduce the velocity by creating terraces. Okay, you can do that like a terrace here. Or the natural means of stabilization, which includes soil binders, plant material that inhibit or prevent erosion by providing a ground cover and forming a dense network of roots that bind the soil. So I think good example of that class is the vetiver grass, because it's a type of grass that is used in uh, soil protection, because its root system, as far as I can remember, can reach up to 3 meters, which can make the soil compact. Okay, then you have what you call the riprap, which is a layer of irregularly broken and random sized stones placed on the slope of an embankment. So this is the riprap class here. Its depth of layer should be greater than the maximum size of stone. And here you have the filtered fabric or graded sand and gravel for the drainage. So another technique is cribbing, which is a cellular framework of squared steel, concrete, or timber members assembled in layers at right angles and filled with earth or stones. Then we have the fifth, a bin wall, which is a type of gravity retaining wall formed by stacking modular, interlocking precast concrete units and filled with voids with crushed stone or gravel. Okay, so this is a bin wall class, and this is a cribbing. Then we have the gabions, which are galvanized or PVC coated wire baskets filled with stones and stacked to form an abutment or retaining structure. So, a good example of this one, I think, if my memory is correct, is when you take a drive there, uh, you know the road going to the Price Hotel. So it's going to SM. If you look at the left side, if you're going to take a drive, you can see some example of gabions being used as retaining walls. Then you have what you call retaining structures. So when a desired change in ground elevation exceeds the angle of repose of the soil, a retaining wall becomes necessary to hold the mass of earth on the uphill side of the grade change. So the types of RC retaining walls are as follows. First, with the gravity retaining wall, which resists overturning inside by the shear weight and volume of its mass. So it has a great mass, so it's shaped like a trapezoid. Then we have the T-type cantilevered retaining wall, which is limited to a height of around 20 feet or 6 meters. Beyond this height, a counter fort is employed. Okay. It's a T-type cantilevered retaining walls. It looks like a T. So take note of what's written here, class. Then the butter, which refers to backward sloping face of a wall as it rises to offset illusion of face leaning forward. Okay. So these are the temperature scale for walls more than 10 inches thick. Then it's a drainage mat with filter fiber or porous gravel backfill. Okay. These are 2 inches weep holes. Okay. Um, 4 to 6 feet on center or perforated drain pipe slope two-way outlet away from the wall. This is structural steel reinforcement. There's the footing, which is to extend below the frost line or below the grade level, whichever is higher. Here in the Philippines, we don't have a frost line because our weather patterns are quite simple. But we do have a relatively high amount of rainfall each year due to the typhoons. This is a counterfort retaining wall, so it utilizes triangular shaped cross walls to stiffen the vertical slab and add weight to the base. The counterfort are spaced at equal intervals equal to one half of the wall height. This is the L-type cantilevered retaining wall which is used when the wall abuts a property line or other obstruction. Okay? So always remember, class, that if your your building or project abuts or adjust or is adjacent to another property, always make sure that your footing will not reach will not breach the property line of the building or structure that you're building, because the other side is already owned by a different owner. Okay, then let's discuss pavements. So paving refers provides a wearing surface for pedestrian or vehicular traffic in the landscape. It is a composite structure whose thickness and construction are directly related to: one is the type and intensity of traffic and loads to be carried, and two, the bearing capacity and permeability of the subgrade. So these are the types of pavements. First, we have what you call the flexible pavement, which consists of units, pavers of concrete, brick, or stone laid on a sand setting bed, which are somewhat resilient and distributed towards the subgrade in a radiating manner. So it requires wood, steel, stone, masonry, or concrete edging to restrain horizontal movement. Okay, so some of the paving patterns here, you have the unit running band. Okay, you have the stack band. Okay, here you have the unit basket weave, and the interlocking basket weave, the octagon and the Roman cobble, the coursed ashlar, and the unit herringbone pattern here, the interlocking herringbone, interlocking basket weave, the turf block, and the random stone. So I hope you can familiarize yourselves thus with different paving patterns, because this might come up in your board exam. So share the paving details. So this is the paving unit on mortar bed set on edge or laid flat. This is the concrete footing. So provide gravel underfooting if frost depth is deeper than the footing. So here in the Philippines, there is no frost. And the paving unit vertically or mortar bed unit may extend up to one half of the paver height from the curb. This is the concrete footing. Okay. So I won't discuss and read the other descriptions last. Okay, so just take a screenshot and try to familiarize yourselves with the different components of your paving details. Okay. Um, the one thing though, class, that you must make sure when you pave is that always make sure that before you lay the paving blocks, that the ground should be properly compacted. Okay. Otherwise, the results would be your paving will form something like a wave. Okay. A good example, I think, class, a good example of quality paving is what you see when you go to other countries, like what I've saw in Hong Kong once. So when you go to it was a temple area, so it was almost paved. So it looks really nice because you can see the craftsmanship and workmanship and level of detail uh, being level of attention being given by the people assembling the stones. So the advantage of using pavers is that mm, I think water there's no problem with water percolation at all. So unlike concrete, when you use concrete, um, the water will just run off. But when you use pavers, there's still a chance for the water to naturally seep into the soil. Okay, thus reducing reducing um, problems in flooding, etc. Okay, so Plus pavers also looks nice. Okay, so this is it for our lecture for this week. So if you have any further questions or clarifications, last, you can reach me anytime in our group page. Okay, so send me a message, an email, and I'll respond to your queries. Okay, so see you next meeting and stay safe.